Hello, everyone. My name is Gaurav Saxena. I would like to welcome all of you for our session, Build an Enterprise-Grade Real-Time Data Lakehouse using Ursa and Apache Iceberg. Over the next few slides, I will share my insights and the challenges running into a real-time data ingestion and the requirements that we get at the enterprise scale. I am delighted to introduce my co-speaker, CJ Go. He is the co-founder and CEO of StreamNative. He is also one of the original creators of Apache Pulsar. And we will talk about how StreamNative's solutions can be used in some of the problem statements that enterprise companies can run into it, and the better way to do your data ingestion as well as building a lakehouse solution. I'll start with a quick agenda. We are going to be outlining here the enterprise needs and the hurdles we usually face in ingesting the real-time data as well as handling the volume. Then I'll hand it over to CJ, who will explain how StreamNative's Ursa engine paired with Apache Iceberg can directly address some of these challenges in the first 2 points that outlined in the slides. It's this slide will resonate with all of you here. At enterprise companies like a Fortune 500 companies, we deal with massive data streams. We have the data from IoT sensors in connected vehicles to a user log data. So in this environment, we can't wait for hours or days to get the meaningful insights. We need real-time processing. However, moving to real-time adds complexity. Traditional batch-oriented ETL pipelines might have been fine at a smaller scales, but they do simply break down with the higher volumes and the velocity that we see today. When you are operating in the scale of Fortune 500 companies, as like an example, automotive industry, these 4 areas are very critical. Regulatory requirements, they are paramount to the industry. It requires strong governance, especially for safety and privacy. And then cost can spiral if you're moving the data between one data streaming platform to other data streaming platform. As far as the scalability, a single software update event across millions of vehicles running on a road can generate a massive spike in telemetry data. So our platform should be able to handle that load. And finally, open standards and interoperability, they protect our long-term investments. To put things in perspective, automotive industry is quickly moving towards 2 software-defined vehicles. There is a projection in next 10 years, 100 millions of vehicles on the road will be connected with the cloud. So the reliability is very important. If you own Tesla or any of the recently built vehicles, you want your vehicles to be better every day. You want over-the-air updates to be performed at a much higher reliability. So you can't say now anymore that, oh, I have to take my maintenance down because I'm doing over-the-air updates. You want your vehicles to be performing at a very efficient scale, right? So traditionally, what happens is that at such a large volume, we rely on multiple Kafka clusters to manage ingestion. But synchronizing them with the downstream data analytics tools is a challenge. Any delay in analyzing that data can directly affect traffic management, predictive maintenance. So with the automotive industry, the use cases, not only the retail use cases. For example, you want to unlock your vehicle. You want to remote start your vehicle. So not only the retail keys, not only the retail pieces, but also your the fleet use cases where you want the diagnosis and prognosis of vehicles to be coming at a real-time volume, so that you can handle the uptime of your vehicles in an efficient way. This is a traditional ecosystem looks like today. So Kafka is a de facto data streaming standard platform. So is Apache Iceberg for managing your open lake table house format. But how do you ingest the data? Usually use either the Pulsar IO connector or Kafka Connect or Red Panda Connect. But there's a challenge between these traditional lakehouse system. What's the challenge? The challenge is basically now you have 2 separate schemas, one with the Kafka topics and one with the lakehouse. So when you're moving data between those 2 ecosystems, and if you run into if there's an error between moving the data, you run into an operational challenges around that. Not only that, if you have the connector, it's a costly. So let's say you have thousands of topics in your infrastructure, and you want to map that to a 1,000 tables, or you want to map it to one table. It goes into a spiral cost of the problem there, right? So we have learned that firsthand that the multi-stage pipelines like this is fragile. It drives up both the cost and latency. Now this diagram shows a typical Kafka-to-lakehouse setup. We will analyze here how the key cost factors derive. There are basically 5 cost factors here. One is your interzone data transfer. Second is on your disk-based application. Third is over-provision compute. Fourth being connector overheads, and the last being the duplicate data copies. I'll break down each of these further in the further slides. So most Kafka users deploy across multiple zones, right? So there's a catch here. Every time an application sends data, the Kafka replicates it between different zones, and apps clients need to also send data to Kafka, multiple Kafka clusters across different zones, leading to additional networking costs. Now the Kafka ensures durability by copying 3 copies of data across zones. So that's great for reliability, but you're paying for those replicas, both in storage cost as well as the interzone transfer, data transfer. In Kafka, the compute and storage are tightly coupled. If you need more storage, you have to scale compute as well, whether you need the extra processing or not. Now moving data from Kafka to cloud storage requires connectors. Now these connectors need extra compute resources, and their network cost each time the data flows through them. If you are leveraging multiple analytical systems, you end up storing the same data multiple times, once in Kafka, and then again in your analytics platform. That's exponential increase in your storage cost. With that, I will pass to CJ Go from StreamNative to discuss a better solution.
Thank you, Gaurav. Hello everyone. I'm CJ Guo, co-founder and CEO of StreamNative. We also have a booth outside. After the talk, you're welcome to stop by our booth. So our focus when founding StreamNative has been kind of focused on simplify the entire infrastructure. So in that way, you can get a really good experience. So over years, we have seen Apache Iceberg stand out as a standard for the modern lakehouse. So first of all, it's an open standard. So open table formats, you are not being locked in by any vendors. Secondly, I think Iceberg is a really good format, support large-scale continuous ingestion. Lastly, it also has a lot of built-in governance features there to ensure high data quality and compliance. So based on these open standard formats, you can everyone is moving towards, okay, just storing 1 copy of the data in your modern lakehouse. You don't need to store 1 copy in Databricks, 1 copy in Snowflake. You can just store 1 copy and share across different engines. But it doesn't solve the problem is that you still have data available in the Kafka, so you still have 1 copy in Kafka for real-time data, but another copy of data in Iceberg for your analytic workloads. So essentially, Ursa is our answer to solve that problem. To kind of reduce the complexity of bridging Kafka and Lakehouse together. So first of all, it's a drop-in Kafka replacement. So it speaks of Kafka protocol. And secondly, it's built on Lakehouse storage directly. So in that way, data produced from your normal Kafka producer will be stored directly on object storage. And we would use the Kafka schema, whether it's Avro, Protobuf, JSON, convert the data into Parquet files. So naturally, our data is stored in Parquet files, and we don't need to duplicate the data again to ingest to the Iceberg. We just put the Parquet files and assemble it as an Iceberg table and register it in the Iceberg REST catalog, so it's able to be discovered through the Iceberg REST catalog, and all your analytic query engines can find it. And so this is a kind of a overview that we have a list of a kind of a status broker, take the Kafka protocol you can produce and consume the data. And we will write it first into a write catalog. This is more like aggregation to aggregate the data coming from millions of topics And then we would do the compaction and write to Iceberg tables. There's a lot of details, probably not going to kind of talk in this talk. Feel free to kind of stop by in our booth. We have the key engineers who are working on this Ursa engine. We are happy to kind of share more details. But I just want to kind of go back to Garav's question about the challenges that he just raised. There is everyone coming to this conference is probably already choose Iceberg as the open table format for building their modern lakehouse, or maybe are looking into building their lakehouse on Iceberg. So you typically have this batch data layer that is doing BI, analytics, and ML, AI-related workloads there, but it's lacking of this streaming capability because you want process data in real time. So you can think about Ursa is not a replacement of Iceberg or any other lakehouse system. It's actually an augmentation layer that we bring into your lakehouse. And that augmentation layer is just like making sure you store data just only one copy, but you are able to consume it either using Kafka API in a streaming way, or you can use it use the Iceberg table API to process it in a batch way. So that's essentially what we call streaming augment lakehouse. Is we are more the augmentation layer rather than the kind of replacement layer there. Although we replace Kafka for sure. This approach essentially is when you bring in the streaming capabilities into your modern lakehouse, it enables you to create what we call universal data product. So essentially, you can store your data just one copy, but you are able to consume it either as a Kafka topic or as Iceberg table. And our approach, you probably hear some of the, I think, Kafka to Iceberg is a very hot topic in the industry, and you probably hear many vendors talking about Kafka ingestion to like Iceberg tables. Our approach is quite different to a certain extent, is that our approach emphasizes more like you just store one copy of the data, and that copy of data, you can consume it using Kafka topics or Iceberg tables, so there's no movement between this Iceberg topic and Kafka topic and Iceberg tables. And some of the other approaches is probably they still implement Kafka using disk-based like storage, but they have an internal mechanism is that copy the Kafka data and rewrite it as an Iceberg table, which still kind of saving to save 2 copies of data. But our approach is more like emphasize, okay, you only have 1 copy of data, and then you are able to expose that copy of data as a real data product that can be exposed as both stream or table. And so, going back into the challenges that Gaurav just described, if you're looking into this diagram, it's a very typical setup. Is you have a Kafka, you have an Iceberg, you're putting some processing logic, some connectors there, and you will quickly find even this is an approach like people trying to simplify by bring in Iceberg topic, but you're still facing. If you're using disk leader-based replication, you still have a lot of this costly data transfer, and you are duplicating data across different, like internally with multiple copies within that Kafka system, and externally you save 1 copy in Kafka and another copy in Iceberg, and you need to handle the complexity of managing the schema between Kafka and Iceberg. So that would give you kind of the challenges in regards to how you can making sure the data is consistent between your Kafka and Iceberg, and how do you manage all the governance policies to make it consistent. And if you're looking into the Ursa approach that we just described here, it just streamlined a lot of these challenges there. Instead of using disk-based replication, we just use object storage as the storage engine. So the broker can write data directly into object storage. And because we can leverage the schema to convert into Parquet and make the data available as an Iceberg table. So this is just one system, speaking of Kafka API for ingestion, but internally store the data as an Iceberg table. And next is if you see the last screen, there's a lot of these cross availability zone traffic there. With Ursa, it's a leadless solution because there's no leader concept anymore, because we are relying object storage for storing data. So any broker is able to take the right traffic. So in that way, your application can just connect to the broker in the same availability zone to produce the data, and the data will write to object storage. So there's no traffic need to cross availability zone, so which can reduce the entire cost. We did a benchmark running a 5 GB per second workload, which we are able to get the entire cost down to $50 per hour. If you're looking into maybe using an open source Kafka, the cost will probably around like $500 per hour, or like even sometimes with up to 1,000. And because it just store one copy of data, there's no like duplication of the copies. It simplify a lot of these operations because you're just operating on the same copy of the data, and also the governance will become really easy, is because you only have one copy of data. The access control, auditing, security, this could be well integrated with the Iceberg REST catalog, which might be Snowflake Open Catalog, Databricks Unity Catalog, and as well as S3 tables also have this native Iceberg REST catalog implementation. So obviously, I think people looking into the last slides will say, oh, this is a good technology, but I already have running Kafka in my production. I have many of the Kafka clusters there already running, and how we can easily transition from existing workloads to Ursa. Essentially, we provide a tool. It's called universal linking. You can think about it as a migration tool, very similar to Kafka Meter Maker, but different from Meter Maker is Meter Maker do the replication over the internet. So it was just replicating data from one source Kafka cluster and writing to a destination Kafka cluster. And our approach is quite different. We'll just read the data from the source Kafka cluster, and we first, because the data eventually will go to the object storage and save in Iceberg table, so we just like replicate data from Kafka and write to the object storage and save as an Iceberg table. So that's the first two steps, and it doesn't force you to migrate your Kafka consumer producer immediately. It actually gives you a chance to, okay, I want to examine that if the system is reliable or not, and then you can use this tool to get the data into Iceberg, and then you can use any auditing tool to making sure, okay, all the replication has no problem, and then you can spinning up a stateless broker, which is the Ursa cluster in green, and then you can start kind of consume the data from these Ursa brokers there. So the data, so any of your existing work that is not being enforced to kind of migrate before you exam. You actually can replicate data and save data into object storage first, and making sure that you examine the data to making sure you're comfortable with this migration before you actually moving your workloads from your source cluster to destination cluster. So this will give you a gradual approach to moving from your existing workload to Ursa, and that would let you adopt this approach with a minimum risk and no downtime. So to put all this together, I think because it's a short presentation, and we want to kind of share a little bit kind of our experience and how we work with Graph and enterprises to kind of solve the challenges that we're seeing using Kafka to lakehouse integrations there. So ultimately, our goal is to give you a much simplified platform that you already have all the data sitting in Iceberg in object storage. We just bring in this augmentation layer to making sure you have one like streaming augmented lakehouse that is able to handle both real-time and batch use cases there. So you don't need to maintain two different systems, maintain different pipelines. And when putting all things together means less component to manage. You can scale much faster, you can stream much faster, and then also much lower cost. And everyone loves lower cost nowadays. So with all this being said, is if like if you like to explore more, we do also have some blog posts, podcast, webinar, and if you can check all these links. And I think the deck will be shared after the conference. And if you want to learning more, we actually have an upcoming more streaming focused conference called Data Streaming Summit. It's a virtual event. Right now, we have about kind of 100 submissions, and I think this year there's a lot of great talks about Kafka, Flink, Kafka Iceberg integration. And if you want to learning a little bit more about the data streaming integrated with Iceberg, you are welcome to check out this virtual conference. It's on May 29th. It's going to be great. And I think with all being said, I want to thank you for everyone attending this session, and appreciate your attention. And we're happy to answer any question in this conference, in this session. But I know lunch is almost ready. So if you want to chat with us more in details, we are also available in the hallway, in the booth. Feel free to grab Gaurav and me. Thank you, everyone.
All right, thank you, CJ and Gaurav. Please make sure to rate the session when you get a chance, and I believe it's lunchtime. Yes. All righty, see you guys in a bit.